Welcome back. In the first part of our conversation, we explored how your curiosity led you into robotics and why building autonomous robots is much more than assembling hardware or writing software. Now, I'd like to ask something that every beginner wonders. What's the reality of working in robotics that textbooks rarely prepare you for?
That's a great question because robotics looks very different in the real world than it does in a classroom. In college, problems are usually well defined. You're given the inputs, the expected outputs, and enough information to solve the problem. Robots don't get that luxury. The real world is messy. People walk unpredictably, boxes get moved, lighting changes throughout the day, sensors produce noisy data. Sometimes GPS isn't available, sometimes wheels slip, sometimes communication is interrupted. A robot has to keep making good decisions even when everything around it is changing. That's what makes robotics both challenging and fascinating.
So, building the robot is only the beginning. Teaching it to handle uncertainty is the real challenge.
Exactly. One of my mentors once told me programming a robot in the lab is easy, building one that survives the real world is engineering. That sentence stayed with me throughout my career.
Many people imagine robots simply following instructions. Is that really how autonomous robots work?
Not quite. Imagine asking someone to walk through a city they've never visited. The first question they'll ask is, where am I? Then they'll ask, where do I need to go? Finally, they'll decide, what's the safest way to get there? Autonomous robots ask those same questions hundreds of times every second. They must constantly estimate where they are, understand what's around them, choose a safe route, and adjust their decisions whenever the environment changes. That's why autonomy is so much more than movement. It's continuous decision making.
That naturally leads to something many learners hear about very early in robotics: SLAM. People often hear the term but don't always understand why it's important.
Exactly. Let's imagine you've entered a shopping mall you've never visited before. You don't have a map. As you walk around, you gradually remember where the entrances, escalators, shops, and exits are located. At the same time, you're constantly figuring out your own position inside the building. You're doing two things simultaneously: building a map and locating yourself within that map. That's essentially what SLAM allows a robot to do. Without it, many autonomous robots would struggle to operate in places they've never seen before.
That's a much more intuitive explanation than simply defining the acronym. What happens after the robot understands where it is?
Then comes another important challenge. The robot needs to decide where to move. Imagine driving home. There isn't just one possible route. Some roads are shorter, some are faster, some are under construction, some have heavy traffic. You naturally choose the best option. Robots perform a similar process called path planning. They're constantly searching for safe, efficient routes while avoiding obstacles and adapting to changes around them. And the interesting part is that this process never really stops. The robot keeps updating its plan as new information arrives.
Which brings us to another interesting question. How does the robot know what's happening around it?
By using multiple sensors, no single sensor is perfect. A camera provides rich visual information but may struggle in darkness. LiDAR creates accurate distance measurements but doesn't recognize colors or text. Ultrasonic sensors are inexpensive but have limited range. IMRs measure movement and orientation but gradually accumulate small errors. Wheel encoders estimate distance travel but can become inaccurate if the wheels slip. Every sensor has strengths and limitations. That's why robots rarely rely on just one.
So, how do they combine all that information?
That's where sensor fusion comes in. Imagine asking five people to describe the same event. Each notices different details. By combining everyone's observations, you build a much more complete picture. Robots do something very similar. They combine information from cameras, LiDAR, IMS, GPS, encoders, and other sensors to make better decisions than any single sensor could provide on its own. One of the biggest lessons I learned in robotics is that reliable decisions come from combining information, not relying on a single source.
Another term people frequently encounter is ROS. Some beginners even assume it's another programming language. What exactly is it?
That's a very common misconception. ROS, the robot operating system, isn't actually an operating system in the traditional sense. Think of it as a collaboration platform for robot software. Imagine building a robot where one engineer writes navigation software, another develops computer vision, someone else controls the motors, and another person handles communication. Without a common framework, integrating everything would be extremely difficult. AROS provides a standardized way for all these different software components to communicate and work together. Instead of reinventing the wheel for every project, engineers can focus on solving new problems. That's one reason AROS has become so widely adopted throughout the robotics community.
It sounds like robotics is really a team sport.
It absolutely is. People sometimes imagine one engineer building an entire robot. In reality, successful robotics projects involve experts from many different disciplines. Mechanical engineers design the robot, electronics engineers develop hardware, embedded engineers build low level control systems, software engineers create perception and navigation algorithms, AI specialists improve decision making, testing teams validate safety and reliability, and field engineers deploy everything in real environments. Robotics succeeds because many different kinds of expertise come together.
We've talked about technology, but what surprised you personally when you entered the industry?
How much time we spend testing. I expected to spend most of my day writing software. Instead, we constantly tested indoor testing, outdoor testing, daytime testing, nighttime testing, testing with obstacles, testing with different floor surfaces, testing after software updates, testing after hardware changes. Every small improvement needed validation because tiny changes could affect the robot's overall behavior. I quickly learned that testing isn't the final step, it's part of the entire development process.
Many beginners worry about learning every new robotics technology they see online. How should they approach that?
Don't try to learn everything at once. Build your knowledge gradually. Start by understanding electronics and programming, then learn embedded systems, then sensors, then robotics fundamentals, then localization, then SLAM, then path planning, then ROS, then artificial intelligence. Each concept builds naturally on the previous one. Strong fundamentals make advanced robotics much easier to understand.
That's reassuring because robotics can feel overwhelming at first. Before we finish this segment, if you had to share one truth that every future robotics engineer should remember, what would it be?
Robotics isn't about building machines that never make mistakes. It's about designing systems that can observe, learn, adapt, and recover when the unexpected happens. That's what makes autonomous robots so remarkable. And that's why every topic you learn, from sensors and localization to SLAM, path planning, sensor fusion, and ROS, plays an essential role in making autonomy possible.
What a fantastic way to conclude this part of the conversation. Today, we've learned that robotics is about much more than writing code or assembling hardware. It's about solving uncertainty through intelligent engineering, collaboration, continuous testing, and systems thinking. In the next episode, we'll move from concepts to unforgettable real world experiences. We'll hear about robots that got lost, projects that nearly failed, funny failures, dangerous deployments, impossible debugging sessions, and the engineering lessons that only experience can teach. Stay with us.